a matrix. Okay, the rank of a matrix is the number of leading non-zero entries or rows in its echelon form, or possibly exactly the same value if you have it in reduced row echelon form. That's acceptable as well. Let's take a quick example. We've got this matrix A reading across. We've got 1, 2, 3, 1, 5, 4, 2, 7, 8. And if you go through and find an echelon form for it, using either your calculator or the Linear Algebra Toolkit or MATLAB or something, then I found the following is unechelon form for this matrix: 1, 2, 3, 0, 3, 2, 0, 0, 0. Now you notice these leading entries I have in red. How many of them are there? There's 2, or you could say there's 2 non-zero rows. In any case, this matrix therefore has rank 2, and we write rank A equals 2. Here's another example. If B is the matrix 1, 1, 3, 2, 2, 6, 3, 3, 9, then B has the following echelon form: 1, 2, 3, and the other rows are zeros. Therefore, the rank of B is equal to 1. Okay, so a simple idea. We will show later that the rank of a matrix is the dimension of both the row space and column space of the matrix, a result we will call the rank theorem. In the case that the matrix under consideration is the augmented matrix of a consistent system, now that's important that it's be a consistent system of linear equations and unknowns, if the rank is little r, then the following holds. If the rank is actually equal to the number of unknowns, then the system has a unique solution, that is one solution. If the rank is less than n, then the system has infinitely many solutions, okay? That's for a consistent system. You got to make sure there exists at least one solution. All right, let's take a quick example here. Suppose I have the following 3 by 4 matrix is actually an augmented matrix. So what I would imagine doing here, I'd have my dashed line or my separator right there, and maybe label the first 3 columns here, x, y, z, and you could imagine what the 3 linear equations are corresponding to this augmented matrix. It'd be easy to find. Okay, now it has echelon form given by 1, 10, negative 4, and then 3, 0, negative 3, 2, and then zeros for the last row. And then if I restore x, y, and z to this, you can see the rank is 2, since there's only 2 non-zero rows, but that's less than 3, which is the number of variables, so the system has infinitely many solutions. Now you should know then that these first 2, the x and y, are what we call basic variables. They're associated with what? Leading entries and rows, in this case 1 and 7. The only variable that is not a basic variable is what we call a free variable. That's actually the z there. And if you actually write the solution to the system here, you can see that everything could be written in terms of z. Let's maybe do that real quickly here, just for a reminder. The first row would be saying x plus 10y minus 4z is equal to 3. The second row would be saying 0x, so we'll ignore that, 7y minus 3z is equal to 2. Thus so. And then you can see the last row, of course, is saying 0 equals 0. And clearly here you can see that x and y could actually be written in terms of z here. Okay, so the number of solutions must indeed be infinite here. Okay, all right.